So I said that number 92, which is a methane ethane mixture. Number 101, which is magnesium chloride sodium chloride mixture. Number 39, which is methanol ethanol mixture. All the same. These are two component mixtures. So two component mixtures, I said, there are two ways that you could solve it. You could solve it, algebraically. You could solve it graphically. Two equations, two unknowns for graphical. Which one do you want me to do? I don't think I'm going to do all three. 101?
Oh.
39?
Do you have an answer key for the practice test?
No. I don't. I never made one up. But we can go through. Do you work through it yet or not yet?
No, I was just working on it, but then I'm only one person in the class, but I want to do 39.
39? 39 is more difficult than 92, though it sounds similar. So what we have is we have X grams of methanol. The first thing is, what is the formula for methanol? Do you know the formula for methanol?
CH3OH.
CH3OH. What happens if you forget the formula for methanol? If you forget the formula for methanol, you can always ask me for what is the formula for methanol, but I would end up deducting a small number of points for that. Plus Y grams of ethanol. Okay, what's the formula for ethanol?
CH5OH.
No. Close. CH5OH. Well, this only has one carbon.
C2H5.
Yeah, C2H5OH or CH3, CH2OH. You could use either of those. We'll just do CH3, CH2OH. Now, if you combine the CH3 and the CH2 together, you'll get C2H5. So we don't know what these X and Y are, but we know that they have to total up to 0.220 grams of mixture. And so how much methanol, how much ethanol? So we have two unknowns, so we have to come up with another equation, etc. This is method one. Well, this is actually a stoichiometry problem, so this is kind of chapter 4. This is a stoichiometry problem occurring in chapter 3. So this is why I was going to give a brief overview of 4 and then come back to this problem in 3. All right, let's look at the graphical method. The graphical method, what we do is we look at the two extremes. Like, on the one hand, we'll do is A, we'll assume that the mixture isn't a mixture. We're going to assume it's 100% methanol, CH3OH. You get tired of writing methanol over and over, so we use abbreviations for this. The abbreviation we use for methanol is MEOH, methyl alcohol. ME is the abbreviation for methyl. So that's methanol. If it's 100% methanol, then all 0.220 grams of this will be methanol. And so we're going to get 0.220 grams of methanol. So what we're doing here is we're just calculating it at the extremes. And then the mixture should be somewhere in between the two extremes, which we can figure out. And so if we have 0.220 grams of methanol, then we need to convert that to what? Well, where would you go for stoichiometry? Well, the plan is this. Produces 0.3520 grams of CO2. So if this mixture were pure methanol, how many grams of CO2 would I produce? And so your standard stoichiometry, this is your standard stoichiometry, grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. You know, just your straightforward, standard, run-of-the-road stoichiometry problem. And so let's figure out the molar mass for methanol. This is why I asked you guys to memorize some of these, so you can quickly calculate the molar masses. Tomorrow's exam is not going to be timed, strictly timed, you know. You should have plenty of time to finish, I think. You know, versus most of the exams I took at UCLA were all timed. You had 50 minutes or 2 hours and 50 minutes to finish. And so it being timed, you have to add the other element, speed. And so you aren't being well trained in speed if I give you the full lab period to finish the test. But you aren't going to need the full lab period, most likely. So let me see how much time I'll give you. But if you have a strictly timed task and it's too long to finish, then you want to be able to do certain things quickly. And so methanol, we have one carbon, it's 1201. We have how many hydrogens? 4 times 101 is 404. And then one oxygen, 1600. So this is going to be 5, 10, 12, 3205. And so 1 mole of methanol weighs 32.05 grams. So we go from grams of A to moles of A, moles of A to moles of B. Now to go to moles of B, we need the balanced chemical equation. And so we'll have to figure out the balanced chemical equation. So I'm going to write it out, CH3OH. This is combustion, so what are we reacting with? And then what are we going to produce? CO2 and H2O. We're going to assume complete combustion. We're going to assume that, you know, it's burning to a nice blue flame rather than yellow. So there's no soot, there's no carbon monoxide being produced. All right, so balancing this, I leave oxygen for last because that only has one element. Everything else has more than one element. And so here, methanol, we have one carbon. The carbons are balanced. Methanol has 4 hydrogens, 3 plus 1. Water only has 2, so we'll double it, make 4 hydrogens here. Okay, now we're going to work on the oxygens. I don't want to change the number of oxygens on the right because I'm going to have 2 oxygens plus another 2 oxygens. So that gives me a total of 4 oxygens on the right. On the left, I have 1 oxygen that's fixed plus N times 2 oxygens, or X times 2 oxygens, whatever variable you want to use. I'll just write N times 2 oxygens. So what this is going to be 1 plus 2N is equal to 4. Therefore, N is equal to what? 3/2. So this is 3/2. But do we like fractions in stoichiometry? No. So what should we do to get rid of the fraction?
Multiply everything by 2.
Multiply. So we're just going to double everything. So this is going to be 2 methanol. This is going to give us 3 O2s, 2 CO2s, and 4 H2O. Now it's balanced. And so what we see here is that the mole ratio is 2 to 2. That is, 2 moles of CO2 are produced for every 2 moles of methanol combusted. So grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. So carbon's 1201, oxygen is 16 times 2 is 32, 32 plus 12 is 44, and then we have the O1 from the carbon. And so this is going to be 4401 grams of CO2 per mole of CO2. So let's go ahead and calculate this next. I forgot my calculator. Sometimes I'll forget to record the morning. So there are two chances to get the recording, but I forgot it. Well, anyway, this is it. So what can we do for the last 7 minutes of class? Were there any questions you guys had? Why don't you work on this? Work on this, and if you're uncertain about the answer, you can ask. I'll tell you what the answer is.
I was kind of confused for the 21 on the old exam.
Okay.
So everything just PPM, so I wasn't sure how to sort of solve that.
You could do the straight dimensional analysis. There's a problem here on the old exam. I made a mistake. On number 30. Number 30, this doesn't contain any oxygen. So eliminate the and oxygen here. An unknown carbon and hydrogen compound was combusted. Okay. No oxygen. So automatically C, we can eliminate it because there's no oxygen. If there were oxygen, I'd have to tell you the total mass of the compound. Number 21, I don't give you all the information there. And so you're missing some information. And so we'll just use dimensional analysis. If we use dimensional analysis, what should we start off with? 1.2 ppm or 1 kilogram of water? I hope I recorded the mixture. But maybe I got it. So I probably missed about 50 minutes or more. So we start off with 1.0 kilograms of water. This is pool water. Pool water, I'm just going to write PW for pool water. 1.0 kilograms of PW, pool water. And then where do we go from here? Yeah, conversion is going to be 1,000 grams per kilogram. This is good for anything, so I don't have to write PW. And so kilograms cancel, and that gives me grams of PW, pool water. Okay, then where do I go?
Moles of water?
No, it's not pure. This water is not pure. What does 1.2 ppm mean? That means 1.2 grams of what? Chlorine. I write chlorine out like this because I don't know that 1.2 grams of chlorine in what form it's in. Is it Cl2? Is it Cl? Is it Cl in some compound? Well, it's Cl in some compound. It's Cl in bleach most likely. And so there's 1.2 grams of pure chlorine atoms in that bleach. For every million grams of what? It's parts per million. So for every million grams of what? Yeah, PW. And so I can get rid of pool water, grams of pool water here. It's 1.2 grams of chlorine per million grams of pool water. And so I want how many, how much chlorine I have. So let's stop here and figure it out. So it's going to be 1 times 1,000 divided by, times 1.2 divided by 1,000,000. 0.00120 grams of chlorine. If I move the decimal, I can move it 3 over, 1, 2, 3. This would be 1.20, or 1.2, times 10 to the minus 3 grams. 10 to the minus 3 grams is also known as a milligram, so 1.2 milligrams of chlorine. And so the correct answer is E. Okay, other questions?
Yeah, can you do
4.
4? Chemical properties of hydrogen and deuterium.
Yeah, the chemical properties of hydrogen and deuterium differ. No? Yeah. No. The elements are defined by the number of protons they have. So both the hydrogen 1 and hydrogen 2 have the same number of protons. 1, and that's the element hydrogen. So both of these are hydrogen.
Does the amount of electrons matter?
Both have the same number of electrons.
Well, because 15 is the same, but it's Na and Na plus.
Okay. So yeah, these two are the same, but deuterium is twice as heavy. H2 is twice as heavy as H1. So that's going to change some of its physical properties and physical characteristics. In the video, do you remember I talked about that video, Can You Drink Heavy Water? Well, what they say in that video is the reason that heavy water, if you replaced 70% of your water with heavy water, then that's going to change certain things. It's going to change the density. Also, it's going to change what we call the kinetics. Sometimes the hydrogen needs to break off. You know, there's protons, what we call proton exchange or proton transfer processes. And if the hydrogen is twice as heavy, it's going to have more inertia. It's going to happen slower. And the speed of certain reactions is very important in biological function. And so it's more of a physical, but that has an impact on chemical as well. The other problem was what? 15. The chemical properties of Na and Na plus differ. Is that true or false?
I said true, but you said, it matters protons and these.
Yeah, let me take that back. In chemistry, the electrical forces are most important. So if you have one proton and one electron, it's balanced, right? But in this case, sodium has how many protons? 11 protons. And this has 11 protons. And so they're the same. But when you look at the electrons, this one has 11 electrons, that has 10 electrons. And so then it's different because electric charges, the neutrons are neutral. And so this is why in number 4, having one extra neutron doesn't make a difference because it's 0 charge. But if I start screwing up with the protons and the electrons, then it's just going to change the properties.
4 is false, 15 is true.
Yes. 4 is false, 15 is true. All right, I guess we're out of time, but I have my office half hour now, so if you have more questions, I'll stick around.
Will you provide the periodic table of the exam?
Yes. You'll have the periodic table for the test.
Are we, is it taking the exam and then doing lab after?
No. Pretty much just the exam. I'll probably do a little bit of catch up and then we'll take the exam. Do you guys have this skin? Were you able to get the Scantron? Again, the skin one? Okay.
The small ones only have 30 questions.
Oh, okay, then do the long one, long form. So I'll stick around for another half hour or more.
Products of combustion, that I think we went over that, everybody's talking about
26. So, CO, CO2, and CO3 are potential products of combustion. You wrote, what, false or true? Or didn't know?
I think false, I think I forgot I went over it, but I don't think it was.
Yeah, a false is correct. This is false. It's because of this. And this is an oxidation state problem. If you look at CO3, what is the oxidation state of carbon in CO3?
That's 6.
Plus 6. This is minus 2. So minus 2 times 3 is minus 6 plus 6. What's the range of oxidation states for carbon?
Plus 4.
Yeah. So carbon can gain 4 to be like neon. So that would be minus 4. And it could lose 4 to be like helium. So that would result in plus 4. So this is the range of oxidation states. Plus 6 is outside that range. And so we figure it's not stable, being outside the range. And so that's why that's false. CO, and CO2 are fine, but CO3 is not.
And I know you talked about the lab experiment 14, the titration. You said because tomorrow is a lab.
Oh, yeah, the titration report you can turn in next week too.
And it won't be any late.
No, there won't be any late penalty for that. I forgot to announce that earlier.
You announced that, I think, last class.
Oh, last class? Okay.
I just wanted to double check.
Yeah, that's correct then. You can turn it in later. We have an exam, and usually during exam days people forget, and so it turns into the same thing anyway. Everybody asks, oh, can I turn it in later? Because they're worried about the exam, so we'll just turn it in later, it's fine. Okay, other questions? Lily?
Yeah, I have a question on the homework.
Okay.
I think it's similar to the last question on the exam, but I just can't figure out what I'm doing wrong, or even if I'm setting it up correctly. 92.
92.
Chapter 3.
Okay, so what did you do for 92?
I assumed 100% of, well, first I did methane.
Okay, so you assumed a 100% methane.
Mm-hmm.
All right.
And then I did the same for
How many grams of CO2 did you get if it were 100% methane?
2.0071.
Okay, and then you assumed 100% ethane?
Mm-hmm.
And how many grams of CO2 did you get for?
2.1419.
Okay. And what was the methane again?
Methane was 2.0071.
Okay. And so the question is, from the beginning or from that point on? Or where did you get?
Well, I'm just getting the numbers that I'm getting when I do the equation.
Mm-hmm.
I'm getting very low percentages for ethane.
Mm-hmm.
And
What is the percent ethane that you get?
well, first I got 0.16%, and then I figured out that I had made a mistake, but then I got 9%.
9% ethane?
Uh-huh.
Okay. That isn't necessarily bad because do you know natural gas has a little bit of ethane in it? Natural gas is not pure methane. Percent by mass. So natural gas contains methane, ethane, propane, butane. And these are the percent natural. Is this percent? I don't know if this is mole percent or mass percent. But methane contains 60 to 90% methane, and then 0 to 20% ethane. And so if you're getting like 9% ethane, then that sounds like natural gas.
Okay.
You know, I don't think it's weird. But we could look. Do you have the solutions guide?
Have a good night.
Thanks.
I have like a Google Doc that someone sent to the Discord, so I don't know if some of the answers are wrong.
Yeah, that's true. Some of the answers are wrong.
So I don't know if it's wrong, but they got 40%.
Did they do it? Okay. Well, we could do this using the graphic method, just to double check.
Did you do it?
No, but I have a full solutions manual. 40% by like mole percent?
No, mass. 40% by mass.
Of which one?
Ethane.
Okay, yeah, that's what they got too.
Okay, yeah. So I'm doing something wrong.
All right, then let's take a look at it. So the first step is you assume all 0.732 grams was methane, right? CH4. Okay, so what we're going to do is we'll do that A, 100% CH4. And then 1201 plus 404 is 1605. So 1605 grams per mole. And then we're going to go, let's balance it, get the balance equation. Methane plus O2 yields CO2 plus H2O. And so one carbon, 4 hydrogens gives us 2 waters. And this is 4, and so that gives us 2 O2s. And so it's a 1-to-1 mole ratio. 1 mole of CO2 per 1 mole of methane. And then it's 4401 grams of CO2 per mole of CO2. So let's just double check this calculation here. 0.732 divided by 16.05 times 44.01. 2.0072 grams. So you got the same, right?
Yeah.
Okay, then B, we'll assume 100% ethane. Should be CH3, or C2H6. And so 0.732 grams of ethane. Ethane, I'm just going to write ET. Ethane. And so 2 carbons is 24, and then plus 6 is 30. 30.08 grams per mole. And then you got the balanced chemical equation? This is CH3, C2H6. We'll just do C2H6. C2H6 plus O2 yields CO2 plus H2O. We got 2 carbons, 2 CO2s, 6 hydrogens, 3 waters. That's 2 times 2 is 4 plus 3 is 7. So this is going to be 7 halves O2. Double everything. We're going to get 2, 7, 4, 6. And so the mole ratio is 4 moles of CO2 for every 2 moles of C2H6. And then 44.01 grams per mole of CO2. And so 0.732 divided by 30.08 times 2 times 44.01. .142 grams of CO2. Is that what you got too? No, it's not. Looks fine. And then, did you make a graph?
Yeah.
What did you put on the x-axis? Percent methane or percent ethane?
Percent methane. Or no, sorry, ethane.
Yeah. You do percent ethane because ethane gives more CO2 per gram than methane. And so we'll do this one here. This will be percent ethane. It's going to go all the way up to, if we have 100% ethane, it's going to go all the way up to 2.142. This will be grams of CO2. And if we have 0% ethane, then it's all methane, so we'll end up with 2.0072 grams. And this will just say straight line. Okay, and then the equation for this is Y is grams of CO2. Grams of CO2, and there's a slope, so we have 2.142 minus 2.0072 grams of CO2 divided by 100% ethane, 100 minus 0. So 2.142 minus 2.0072 divided by 100. So this comes out to 0.001348 grams of CO2 per percent ethane times the percent ethane plus the intercept, 2.0072 grams of CO2. So we'll solve for the percent ethane. So we're going to plug in here how much CO2 we got, 2.064 grams. So we'll do 2.064 minus 2.0072 equals, divided by 0.001348. And so I get the percent ethane is equal to 42.143% ethane. And that means I'll have 57.857% methane. And then do it to the right sig figs, which looks like we're probably going to be allowed not that many, you know. So it's like 42% ethane, 58% methane. Is that what the book got? Yeah. So it's just a lot of calculations, so it's easy to. You just double check it and think. Then.
Yeah, I put in the wrong number for the
Okay.
grams.
Yeah, if you do this two equation, two unknowns, then it's a lot easier to get messed up in the calculations.
So all the experiments and people that we need to know are just the ones that you talked about?
Oh yeah, the people. Yeah, like you said, Rutherford, gold foil.
Yeah.
Millikan, oil draw. J.J. Thomson, cathode ray tube. Those three.
Do we need to know, like, what they learned? Like, J.J. Thomson discovered the electron, and
That's, yes, you need to know, J.J. Thomson discovered the electron.
and then
Millikan discovered what?
he discovered the charge.
Charge.
Electron.
And Rutherford discovered what?
Well, the nuclear atom model.
Yeah, that's all you need to know.
But he also discovered the proton.
Yeah, we don't need to know that.
And we don't need to know neutron.
No.
Um,
But it's important because, I mean, those were important discoveries as well. You know, Chadwick and Rutherford. But I'm not going to test you on that.
And then, other than Dalton's law of multiple proportions,
Oh, yeah.
what laws?
Well, you need to know Dalton. It's not Dalton's law of multiple proportions, it's the law of multiple proportions. Dalton is the atomic theory, Dalton's atomic theory. You need to know the law of constant mass or conservation of mass, law of constant composition, law of multiple proportions.
Which one's constant composition?
Constant composition is that water is always H2O.
Oh.
Anywhere you go, has the same composition.
And what was Dalton's atomic theory?
Dalton's atomic theory was based on the observations. When you look at the law of constant composition and the law of conservation of mass, there must be a finite limit to the elements. That finite limit must be the atom. Otherwise, if you have no limit, that is, if matter were infinitely divisible, then you would expect small variations in the composition, by having a little bit more, a little bit less of one element versus the other. But when you have such a simple, ratio, or constant composition, they didn't know the ratios at that time, except the mass ratios. But when you start looking at atoms, then it boils down to simple whole number ratios, which makes sense if you had atoms. It doesn't necessarily make sense if you have infinitely divisible, because you can have any amount. It's like continuous versus quantized. Matter was quantized, not continuous. That's why it led to those observations. So that's Dalton. The atoms were proposed well before Dalton, but there was no evidence in support of it. It was just a hypothesis with no experimental observations to support it. And so this is why Dalton's credited, even though atoms were proposed by, centuries before Dalton came along. Not Dalton.
Were all the laws Dalton's?
No.
Well,
No, law of conservation of mass came from Le Chatelier, not Le Chatelier, Lavoisier. But I'm not going to make you memorize the name. The conservation of mass came from Lavoisier. Constant composition came from somebody else. It was before Dalton's time. The atoms came from somebody else.
But they seem take the label.
Democritus, or was it no? Greek philosophy. These people, Democritus, yeah.
Because I'll look up Dalton's law of, and he's got it says multiple proportions, constant composition, partial pressure. Did he just steal or does it mean nothing?
That this all it's all associated with Dalton's atomic theory. It's not that he didn't discover. A lot of science is really, did Dalton really discover it? No, but he's credited with it. When you look on Wikipedia, who comes up? Atoms, Dalton. But Dalton didn't really propose it. And so it's the same thing. Conservation of mass was known well before Dalton's time. But maybe they credited him, Dalton, but it was Democritus who proposed atoms. At least in the first written stuff. But Democritus didn't have any evidence to support his hypotheses. So that's the big difference. In the scientific method, we need some kind of supporting evidence for your hypotheses. You know, otherwise it's just, it's not science, you know. It's like, this is the point with the elixir of life. The elixir of life had no supporting evidence for its existence. And so you could spend, you know, your life looking for the elixir of life, but what evidence do you have in support that the elixir of life exists? There is none. So that's not science then. And so Dalton, this is why Dalton's credited with coming up with the first meaningful, but there are probably contemporaries of Dalton's who also thought the same, you know. But Dalton was the first person to put it together with the law of constant composition and the law of conservation of mass. He was the first to say those are two laws that are in support of my hypothesis. And so that's it. But it's not such a big deal. If you call it Dalton's law of conservation of mass, it's okay. You know, science is just built up. You know, this is the thing about science is you work. You don't start and reinvent the wheel each time. You just, you know, you just build up upon other people's discoveries. Otherwise, you'll never get anything done. So I wouldn't worry about it too much, but you should know Dalton, atomic theory, and some others. I mean, there are other names that you should know, Schrodinger, Heisenberg, this kind of stuff. But those will come later again. But for sure, J.G. Thomson, Millikan, Rutherford, those show up on standardized exams. Those names, Heisenberg does, Schrodinger does too. Okay.
I was wondering about the question number 4 on the practice test. I was thinking about it, the difference between plutonium and deuterium, if it's a difference in chemical properties, and wouldn't the densities affect the kinetic energy, which could affect chemical reactions?
The speed of chemical reactions, they just happen slower, but it's the same chemical reaction. So for example, you can burn hydrogen, but let's say if you're burning deuterium, only heavy hydrogen, maybe kinetically it's going to burn slower because, you know, it's heavier. It's heavier, it moves slower. Although, it moves slower, but it's more massive, so it's going to carry the same, what we call momentum, same energy, that kind of stuff. But it's going to change things, you know, it'll change things, but it's still going to be combustion. It's still going to burn in oxygen. It's just going to happen slower. So that would be more physical than chemical. But you could argue both ways. You know, nobody's going to say, no, you're wrong. If you call it chemical, they are different chemically. You know, for the most part, if you're going to pick one, it's not black and white. If you're going to pick one, I'd go with the same, because does hydrogen undergo combustion? Hydrogen gas? Yes, regardless of what isotope it is. Is hydrogen in water, and is that water going to satisfy your thirst? Yes, it is. You know, so for the most part, they're the same, but there are going to be differences. And if you call those differences chemical, nobody's going to argue, because in a way that is chemistry. Kinetics of the reaction would be a chemical property of how fast these reactions occur. So it's not so black and white in that sense, but if you're going to pick the best, I would say they're more similar than they are different.
Yeah.
Chemically. Physically, they're totally different. I mean, one's going to be so much heavier than the other. And so if I asked for physical properties, you'd say yes, they're different.
Okay. Because I was talking to some friends this morning when we were studying, and I forget who, but they were talking about the fact that they don't have any difference in charge, which kind of makes sense, because isn't chemistry dealing with the electrical properties of
Yeah,
matter?
right.
Okay.
It's strictly electrical properties. So hydrogen has 1 proton, deuterium has 1 proton, and they both have 1 electron. And so there's no difference in charge. And chemistry is all electrical, and so if the charges are the same, then you expect them to behave the same electrically. And electrical is chemical properties, so the chemical properties are the same for the most part. This is something that Colin was asking as well too, is this one. What number was that?
It's 15.
15. Yeah, here, both of these have the same number of protons, but the number of electrons is different. And since chemistry is all electrical, then they're going to behave differently because they have different electrical environments around them. And so sodium is different than sodium ion.
Yeah, that one is a little more straightforward
Yeah.
for me
Okay.
to understand. The other one, I mean, I get it now.
Yeah, a neutron, I was telling Colin, a neutron, a neutron, what's the charge on a neutron? 0. And so you have one neutron in here. The neutron's not going to be influenced by any, electrical force. It's got no charge. If you feed a neutron through a mass spectrometer, it's not deflected at all. You can't weigh neutrons in a mass spectrometer. And so how did they figure out how much a neutron weighs? You know how they figured out how much a neutron weighs?
Was it through observation?
They weighed deuterium. Deuterium consists of one proton and one neutron, and then they subtracted the mass of the proton to get the mass of the neutron. But then again, isn't there the mass defect?
Yeah, that's what I was gonna say, because
Yeah.
if they calculated it. then-
Yeah, but then somebody might argue, well, the mass defect is to hold protons together. If you have one proton and one neutron, then there's no electrical repulsion. And so there shouldn't be much of a mass defect. So you can say the mass defect would be expected to be negligible because there's no protons you're forcing together. And so maybe that's okay, and that's how they got the mass of the neutron, because that's how they got the mass of the neutron. They subtracted the proton from it. But that wouldn't work for other things, because of the mass defect. And so that would be kind of a more advanced problem, This would be something like I say there's a challenge problem. So that might be, a challenge problem on a test that you might see in the future. How did they weigh the neutron? Or they might tell you this is how they weigh the neutron, but is mass defect going to be an issue here? And so these are the types of things you might be able to answer if you thought about it, or things like that. But not so easy just right off the bat to think about that, Because it is kind of a weird problem if we were using a mass spectrometer to weigh things. But anyway, that's but does that make sense?
Yeah, it does make sense now. I get it.
I was just gonna ask, really quickly, I wanted to go through, most of the problems. Or at least the ones that.
All right.
First of all, with one, laws being the ultimate goal, that's false. But are theories the ultimate goal?
Yes.
But then could you say, with the two-pronged approach, you start at theories and then you go towards observation? And in that case, your goal is observation?
Okay. Yeah. That's also a goal too. But ultimately, we would like to know the theory, because the theory will allow you to predict those observations. So without the theory, could you predict those observations? With the law, you can make predictions, but the law is sometimes not as comprehensive as a theory.
Okay. 3, I said it was infinite.
That's correct.
Okay. 6, I said it was false because nuclear forces are stronger than electrical, right?
Yes.
9, is that a typo or?
That's a typo, but you just say none of these.
Okay.
If this were cubed,
They're all cubed.
then it would be A.
Okay.
If these were cubed.
11. Is it the nuclear forces holding the electrons to the nucleus?
No.
It's holding the protons, right?
Right, it's holding the protons together in the nucleus. What's holding the electrons to the nucleus are Coulombic forces, electrical forces.
Okay, so if you switch electrons with protons, that's true.
Yeah.
Okay. 13's a trick question, right? It's the formula is telling you the mole ratio, because I mean it's true that it is H2O is 11.2 by mass and 88 by oxygen, but you know, just looking at the formula, it doesn't tell me.
No, yeah. You'd have to calculate these based on the formula. The formula just tells you have 2 hydrogens for every oxygen atom, or moles.
Wait, so that's false?
Well, this is a bad question.
Yeah.
It could be true or false, depending on how you interpret this. So this one, yeah, this is not such a great question. So if you wrote true, because this is true, that's fine. If you wrote false, because the formula means 33% oxygen, 67% hydrogen, then that's fine too. So this problem, 13, throw it out.
14, I think it is combustible, but not electron rich. Because, I mean, well, it's
moderately electron.
but it's zero charge, but, you know, if you look at the acetate ion,
It can go up to like -4, so
Yeah, acetate, the thing with acetate is CH3COO minus. If you look at the 2 carbons, they're quite a bit different. If you look at the first carbon's -3. So -3 can go all the way to +4. That means we're losing 7 electrons. Is 7 electrons a lot of electrons, or not that much? It's a lot. And this one is +1. If this one's +1, this one can go to +4. So this one's going to lose 3 electrons. So altogether we can lose 10 electrons for one acetate. And so is that not many electrons, or is that quite a lot? That's quite a lot of electrons. I mean, it's not as many as, let's say, methane. Methane can lose 8 electrons because this is -4. -4 going to +4 is 8 electrons, but still, that's 7 electrons. And so this is why, you know, it is somewhat electron rich. I wouldn't call it as rich as something like methane or ethane, but it's not as poor as oxalic acid.
yeah.
And so this would be true. I would write true for this.
So you know, to see how electron rich something is, do we
Mhm.
really have to, like, you know, make the formula, or like write out the?
No, you have to know the range. The range for carbon is between -4 and +4.
Yeah.
Which side is it on? Well, one is -3. Would you call that rich?
Yeah.
And then the other is +1. +1 is maybe a slightly poor.
Mm-hmm.
And so on average, I would say it's just medium rich,
Okay.
you know.
Well, but also, you know, to find out that one's -3 and one's +1.
You could also do an average. You could do the average oxidation state as well. If you did the average oxidation state, acetate is C2H3O2 minus. So +1 -2. So that's -4 + 3 is -1. And so this has got to be what? -2. Wait, -4 + 3 is -1. So I guess this is 0. Is that right?
yeah.
0 + 3 -4 -1. Yeah, maybe I got those wrong. here. -3 plus 1. No, I'm sorry, this is plus, not plus 1, this is +3. +3. And so the average, sorry, this is +3, so the average is 0. So if the average is 0, we still can lose 4 electrons. So we can go from 0 and we can go to +4, that's 4 electrons for each carbon. We got 2 carbons, a total of 8 electrons. So losing 4 electrons, what would you say? That's kind of in the middle, right?
Yeah, because you can also
Yeah.
use for it.
Well, it can gain 4 electrons, you're right about that. But when we're talking about combustion, as far as combustion goes, it's pretty decent.
And the sodium doesn't matter? Like, why don't I account for that if it's, you know...
Sodium
average
can't
plus
lose any more electrons. Combustion is you're reacting with an oxidizer. Can you oxidize sodium any further?
No.
No. So the sodium ion does not burn. So we ignore it. It's already hit its max.
So is it more accurate to, you know, decide whether something's rich or poor based on how many electrons it can lose, not its net charge?
Right. Where it is in the spectrum, that's how you decide.
Okay.
The situation is you can burn things that are a lot less rich than that. I did the oxidation state for oxalic acid. For oxalic acid, it's +1 for each carbon, and oxalic acid still can burn, not very well, but it can just lose 1 electron. That would be electron poor, but it'd still be combustible.
So it's on topic 22, which is electron poor. I didn't really, you know, think about it very much, and I just said that the A was poor. So it was plus.
It's false.
That's false.
Yeah. That's wrong. B is electron poor. You got to do whenever you do electron poor, electron rich, you have to do the oxidation state. A you can burn in a fire. B you cannot burn in a fire.
Because nitrogen in B is +5.
That's maxed out. +5 is maxed out. It can't lose any more electrons.
So that's max poor.
Yeah,
Okay.
that's electron poor. And then ammonium is max rich. What's the oxidation state of nitrogen and ammonium?
Or -3.
-3 is max rich. So B is electron poor.
Okay.
A is electron rich. A can burn. So if you have ammonium chloride, it would burn. It would form oxides of nitrogen, which you wouldn't want to breathe in, but you could burn it in the hood. Okay. Well, what else do you have? Because I have to leave pretty soon, actually.
Do you have anything else?
Yeah, on the homework, I know we're not gonna be tested on this, but there was one, organic nomenclature question.
Okay.
So if I can find it. Post it. I think it was number 82. Let's see.
All right. 82C. We have this one. Usually, red, I guess this is red here, is oxygen. This kind of brown one is, do you know what element that is? Bromine, yeah. And so what we could call this is, we call this, how many carbons in the chain? 4, so it's bute. And then are there any double bonds or triple bonds?
No.
So it's butane. And then we have a bromo. And so, but we could have bromo on carbon 1, or we could have bromo on carbon 2. If we had bromo on carbon 3, it would be the same as 2, because we just number it the opposite direction. And if we had a bromo on 4, it would be the same as 1. So is this 1 bromo butane or 2 bromo butane? 1. And so the answer for this one would be 1 hyphen bromo butane.
So you have to, with the, what is it, like, element substituents, you have to clarify, even if it's on the end?
Yes, even if it's on the end, because there's 2 possibilities for this one. Like something like propanol, people would assume, if you're talking about propanol, it's on the end. If you're talking about isopropanol, then it's not on the end. You know, sometimes you can just make the assumption it's on the end, but in this case we wouldn't, because if you just said bromobutane, then people wouldn't know. Are you talking about 1 bromobutane, or are you talking about 2 bromobutane? You know, you can't automatically assume it's 1 in that case. And so you would have to say 1 bromobutane.
And for like the functional groups, like hydroxides, carboxylic acids, those you just assume that they're on the end unless you
Yeah,
clarify.
right. The functional groups are going to be on the end. So the alcohol is on the end here, alcohol is on the end here, carboxylic acid group is on the end here. It could be at the beginning too. It doesn't have to be at the last, it could be at the first, but it's got to be on one of the ends. There, it's going to be, oh, this is carboxylic acid here. This is an alcohol. Now this, well, the carboxylic acids have to be on the end. There's no other way, but the alcohols need not be on the end. You know, a normal alcohol will have it on the end. So this is why we call it N-propanol. It's normal propanol with it at the end, like you'd expect. But this is not. This is on carbon number 2, so this would be called 2-propanol. Or no, this is not prop. What is this? How many? Pentanol. This would be 2-pentanol or 4-pentanol. If we number it from here, 1, 2, 3, 4-pentanol, or from here, 1, 2.
Oh, you can go either way?
You can go either way, but we always pick the smaller number. And so what's the smaller number? 2. So this is 2-pentanol.
And for D,
Yeah.
that one I originally put 2-chloro.
No, you number it from the highest functional group. The highest functional group would be the carboxylic acid here. So this has to be carbon 1, because this is the dominant functional group. So we'd have to number it from here, 1, 2, 3. This would be 3-chlorobutanoic acid. We're not going to be dealing with any of these kind of things, just the simple ones. So I want you to know, like simple, like hexane, you know, is a common solvent and other things. But this is not so simple. There are other ones where we don't have to number it. Like today we looked at trifluoroacetic acid. We don't have to number that, because there's only one place you can put that many fluorines on in acetic acid. So we wouldn't call it like 1, 2, 1, 1, 1 trifluoroacetic acid.
Yeah, that would be a little...
We're not going to get into that.
Okay.
Okay.
My last thing, just to check, there's a number 23 on the practice.
Okay.
I said D.
Circle species most electron rich. You circled D?
Yeah.
Yep. D is correct.
Nice.
D, out of all these, D would be the most flammable, the easiest to combust. So the easiest to burn would be ammonia, followed by carbon monoxide, followed by chloride. B and C won't burn unless you can strip the electrons from oxygen. But they definitely aren't going to burn in oxygen because oxygen versus oxygen will result in a draw. Do you have some more questions, Lynn?
Just like generally, are you gonna put much stuff from like the lectures you've done in the labs or more stuff from the chapter?
Lectures that I've done in the labs for what topic?
Like the lecture you did on Monday.
The lecture I did on Monday was chapter 3.
I don't know, it was a lot about like reactions, acids, bases.
No, that's going to be not on this test, the next test. You're talking about KW, I mean not KW, the water, that when I was talking about that, and acid-base reactions, that kind of stuff. Actually, that's going to show up later, on a later test. Although the water stuff, the water autoionization isn't really going to you're not really going to see that. The only reason I brought that up is because people call water a non-electrolyte, but in reality it does break up. But it breaks up to such a small extent that we're still going to call it a non-electrolyte, even though partially. And so the word partially is what I was getting at. What does partially mean? You know? And it's not so clear cut. There's no solid definition of what partially means. So.
But stuff like standardization or like primary standards.
Primary standards, standardization, you need, if I were to give a lab practical, for sure you'd need to know those. On this test, I really should, because it's still, people should know what a primary standard is and standardization is, but I'm not. If I do give something from the lab that's directly a lab topic, then I'll tell you, you know. Some things like, it won't happen on this exam because we didn't get to solution dilution. Solution dilution is chapter 4, but you'll have like a solution dilution even though we did in the lab, it's also discussed in the lecture. Titration calculations, talked about in the lab, but it's also discussed in chapter 4, you know, or chapter 5. And so that type of stuff you'll need to know. But primary standard is not discussed in the lab manual, and it's not discussed in the textbook. So I've thought about it. I've thought about putting a lot more lab questions because a lot of people don't pay much attention during lab for that kind of stuff. But I'll warn you if I do. On this test, don't worry about it. No primary standard.
Okay.